This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right, good morning, everyone. So today we will continue going deeper into analysis of linear systems. Yesterday we talked about Laplace transform. This afternoon in tutorial we will do a few examples of Laplace transform. And today we will talk about several very important aspects of analysis and design. We'll talk about poles and zeros of a transfer function or a system. Then impulse response of linear time invariant systems, and we'll consider first and second order systems and spend a bit of time talking about them because they arise often in analysis and design. There is a bit of material to cover, so I will try to go quickly over some things. Please slow me down if it's too fast. Okay? So first I'll motivate the material and then introduce and talk about pole zeros. We already introduced them in the previous lecture, but we will just now revise them a bit more, and we will talk about how poles in particular affect the response of the system. So we will talk about impulse response of linear time invariant systems, and we will go through all possible cases. If you remember, in partial fraction expansion, we can obtain certain terms which look similar, right? Now, we want to basically look at all possible inverse Laplace transforms of these terms in partial fraction expansion, because these terms would contribute to solutions of linear systems in impulse response, step response, etc. So, and then we will actually go even deeper, and we will consider first and second order systems. These are like main building blocks in analysis. You need to know this material very well, because responses of any systems can be related to this material. So this is very important. And then we will just summarize what are the situations for general systems? What sort of responses can you expect in general systems? You need to know this material very well. So this is all about analysis, that you would need to use it in design, right? So it's a step up from what I will talk about today. Right? So this is very important. You must have seen this material already. So I'm still summarizing things that you probably saw in signals and systems. But it's very important, so I urge you to revise this very carefully. And then we will go to conclusions. So why do we spend time talking about this material? Well, first, it's very important to understand how zeros and poles affect response of your system. Later on, we will see that we will be able to connect things like properties like stability to locations of poles in a complex plane. Similarly, for second order systems, we will present precise formulas that will tell you where locations of the poles should be to achieve certain overshoot, rise time, settling time. So we can really, through design, by placing poles of the closed loop system in a certain region of complex plane, we can affect the step response of the system. So we are talking about design at this stage. Why this is also important? Well, suppose you perform an experiment. So you apply a step impulse to your system, and you just record how the output changes, in this experiment, right? If you see a particular shape of your response, you might be able to guess how many poles, how many zeros the system has, and also whether these poles are complex conjugate or just real. So through an experiment, if you understand all this material from today's lecture, you can really guess the model. You don't know exactly the parameters in the model, but you might say, well, it looks like a first order system response, or it looks like a second order system response. So you can really figure out qualitatively what sort of model you need to use to model the system, just from a single experiment, if you get lucky. Right? So, I mean, complex models may have complex responses, so this won't always work, but in many cases, you can actually guess the model. Now, as I said, a step response design specification can be related to locations of poles for second order systems. We will look at this issue in detail in the next lecture. We will say, well, if you want overshoot such and such, your poles should be in this region of complex plane. So we will be able to translate time domain specifications in terms of step response features into locations of the closed poles of the system. So that's a very powerful sort of design approach. And also, as I said, it's possible to identify a model from an experiment. So such a step response. So all of these things are really foundations of design that we will be concentrating on in the subject. So this is very important. So let's look in more detail at poles and zeros. So last lecture we introduced the transfer function. So transfer function for systems we consider this subject are typically given by rational functions. So we can rewrite this rational function in this manner. So this and that is exactly the same. So these pi's, they actually denote exactly this product from s minus alpha 1 to s minus alpha n. This is just shorthand writing of exactly what's in the denominator. You also have this constant k, which is like the gain of the system. So alpha k's here are poles, beta k's are zeros in the system. Right? These if all a k's, b k's, so coefficients in these polynomials are real, then alpha k, beta k are either real or complex conjugate. Whenever you find a complex zero, its complex conjugate will be also zero, similar to the poles. So we call beta k zeros and alpha k's are poles of the transfer function. So we would often denote these poles and zeros of various transfer functions in this manner. So poles would be typically denoted by crosses in the complex plane, and the zeros would be typically denoted by circles in the complex plane. So in this case, the first example, you have 0 at 1, so that's that blue dot. So it's a real 0 at point 1, right? And there are two poles, one at -1, one at -2, and they're represented by these crosses. In this case, you have 3 poles at -1, right? And they're all presented by like one sort of cross, but there is a multiplicity 3. And in this case, you also, in this second example, you have 2 complex conjugate zeros that are represented by circles. This sort of notation would be especially useful when we look at the technique of root locus for design. So root locus would use this convention all the time. So poles and zeros, it turns out that poles and zeros determine all crucial properties of the system. First, the qualitative nature of the step and impulse response. So if you think about, so what would be the impulse response? The impulse response would be inverse Laplace transform of the transfer function. We learned that last lecture. So inverse Laplace transform of the transfer function is the impulse response of the system. So if you want to find in time domain what impulse response is, we first need to take partial fraction expansion of the transfer function. Now, partial fraction expansion residues will depend on both poles and zeros. Both poles and zeros. Residues in the expansion depend on both poles and zeros, as well as this constant k, right? And then the denominators in partial fractional expansion depend only on poles. Right? But both zeros and poles affect what sort of response, impulse response we would get. Because the impulse response would be sum of responses corresponding to each of the poles. Right? So basically qualitative nature, whether you have a sinusoidal response, whether you get a periodic response, would depend, or some of those would depend on poles and zeros of the system. Also, quantitative nature of response depends on poles and zeros. Obviously, quantitative nature also depends on this constant k that just scales the response. They can just multiply by k all the terms in the partial fractional expansion, right, to get the impulse response. Now, also, overshoot, rise time, settling time, they all, all of these features of step response are affected by locations of poles and zeros, as well as the gain. Now, system stability is related to poles. We saw already in the last lecture, we mentioned it, that if all poles are strictly in the left half plane, then the system is stable, right? Okay. So also you will see later on, and this is something that you probably didn't see in similar systems, we will see that if a plant has an unstable zero, that will impose a fundamental limit on what's achievable with step response with any linear control that you apply to this system. So if you have, just imagine you have a plant with unstable zero, and then you are trying any linear control that stabilizes the system, you will see that the step response would necessarily have an undershoot. So you can't get rid of undershoot, no matter what control you use. That's a fundamental limit to performance that is directly related to zero plant. We will learn about that more in coming lectures. So in any case, all of these are very important for both analysis and design, fundamental design. All right, so now we would like to dig in more into the details of responses of linear time and linear systems. I will talk about impulse response mainly, but step responses, the story is the same. So there are very few differences between analysis of impulse and step responses. I will mention what those differences are, but I will concentrate on impulse response mainly. All right, so when we talk about impulse response, well, we have to start from the transfer function, and the first step, as I said already, we need to expand this into partial fractional expansion. This is not just because of Laplace transform tables. In this lecture, it would help us to understand what sort of response, impulse response we get, because the impulse response would be a sum of responses corresponding to each of these terms. So we will just add them up. So sometimes, if you have a complex conjugate alpha k, you may have a sinusoidal response or part of response. If alpha k is real, you may have a periodic response. In some cases also, we just have constant here, plus just some constant. That's the case when n and m here are of the same, they are equal, so there's the same number of poles and zeros. Then you might have also impulsive part of the total response. So systems, we call these systems direct feed-through, or they are proper but not strictly proper. Proper systems are systems that have more poles than zeros, so strictly proper, and just proper systems are the ones that may have the same number of zeros and poles. So look, in any case, you start from a transfer function, you want to find an impulse response. We can rewrite this, if we have repeated poles, either like that, or if we have distinct poles, we can write it like that. Now, taking inverse Laplace transform of this would mean that the impulse response is a sum of some functions. So we now want to look at what sort of functions we can get, in this sum, right? So I take inverse Laplace transform of this, and I will get a set of different functions. I would like to understand better what sort of functions I can see, and then in the end you just need to add them up. So we want to go through all possibilities. So we understand what sort of functions we can get when we take inverse response, inverse Laplace transform. So what are the possible possibilities? Well, you can have polynomial functions in time. When I talk about here functions, I always mean functions of time. After taking inverse Laplace transform, we get functions of time. So you can get polynomial functions of time, you can get exponentials in time, sinusoidal functions, and also their products. Right? You cannot have a product of a sinusoidal function with an exponential function, either increasing exponential or decreasing exponential. You can have a sinusoidal function multiplied by time, or time squared. So all of these possibilities are there. Now, what we want to do is, we want to understand when do we get polynomial functions, when do we get exponentials, when do we get sinusoidals, when do we get their products. All right? So that's the main sort of thing. Why do we do this? Well, we want to understand in detail impulse response of any system. Right? So we want to dig deeper into it. All right, so here is a summary. So when you find a real, let's say, isolated real pole, you would get an exponential term like this. Now, alpha is a real number, and alpha can be either positive or negative. It can be also zero. So if alpha is positive, this will blow up. You will have a function in your response that blows up in time. Right? As time grows, this function grows. If alpha is negative, this function would converge to zero. If alpha is zero, this function will just be equal to 1. Now, if you have repeated poles, and by the way, when I say here n times repeated pole, I mean if there are two poles, I mean it's repeated once. Right? So that's how I count them. So if there are two poles, I say it's repeated once, because there's repetition once, one repetition. So if you have repeated poles n times, then you have this polynomial, like t to the power n times exponential. That's due to repeated real poles. If you have a conjugate pair of complex poles, if they are not repeated, you get terms like this. It's exponential times the this cosine. Now, sigma would correspond to the real part of the poles, and omega would correspond to the imaginary part of the poles. We will see that in more detail. And then when we have n times repeated conjugate pairs, we will have exponential times the polynomial, like t to the power n. And I count poles in the same way. So look, this is already, giving you almost all possibilities. Now, if the transfer function is proper, but not strictly proper, in other words, we have the same number of zeros as poles, so n is equal to n in the transfer function, then you would also have constant term in the partial fraction expansion. And that constant term, when we take inverse Laplace transform of a constant, that corresponds to that constant times the Dirac function when we take inverse Laplace. So that's why when you have proper but not strictly proper, you would get impulsive part of the total response. So what this tells you now, given any system, the impulse response of any linear system would consist of a sum, weighted sum of functions that look like this. This goes through all possibilities. All possibilities. Note here that if sigma is positive, then this exponential part would dominate the response, and this would blow up as time goes to infinity. Because exponential functions grow faster than polynomial functions or cosine sines. If sigma is negative, this whole product would tend to zero. So sigma would be the real part of the pole corresponding to this term. So what does this say? Well, if I have a partial fraction expansion like this, each term in this partial expansion would correspond to one of these functions here multiplied by some coefficients. What coefficients? That depends on residuals in your partial fraction expansion. So you need to know this very well. You need to know this very, very well. So I will present at the end, at the very end of the lecture, different possibilities. But what we will do now, we will consider, in more detail two simplest cases. The simplest cases are when partial fraction expansion here turns out to be just a single term with a single real pole. Right? This pole can be positive or negative. That's the simplest case of a partial fraction expansion. And another simplest case is when we have second order system, but we have complex conjugate poles. So that's a second order system response. So what we want to do in the rest of the lecture, we will be concentrating more on the first order system with a single real pole. What is the response? We want to plot it, we want to talk about its properties. And also about the case when we have complex conjugate poles. So the system is second order and we have complex conjugate poles. These are, like the simplest cases, right? Obviously, for your really understanding of the subject, you need to understand that in general, we will be adding things to get the response of that particular system. But going through these two cases is very insightful. All right, so let's just consider a simple example. So this is a transfer function. Now, if you, use partial fraction expansions, you will get, so you can show that the transfer function can be rewritten in this way. So if you take inverse Laplace transform of this thing, which is now partial fraction expansion of that, inverse Laplace transform is the sum of inverse Laplace transforms of each of the guys. So what is this? Well, that's inverse Laplace transform of that guy. What is this? This is inverse Laplace transform of that guy. If you go to Laplace transform tables, you would find exactly that this corresponds to that. There is 2 missing here, sorry, so there should be constant 2 due to this guy. And then you have -1. This is basically inverse Laplace transform 1 over s is step function. So it's with minus sign. So there is a typo here, sorry about that. So look, this is an example of what I was saying before. That impulse response of an arbitrary system would be a sum of functions that I already went through. I gave you all possibilities of these functions. So this is just one example. When we have repeated poles, you get terms like this, and these terms would correspond to terms like this, or terms like that, if alpha is complex conjugate. When alpha is like sigma plus j omega, then you would get this sort of terms when you take inverse Laplace transforms. All right, and I already mentioned that response is still dominated by exponential terms because exponentials grow faster or decay faster than polynomials. So even when you multiply with polynomials, like t to power n times exponential would eventually dominate the behavior. So we really just need to look at exponential to understand what happens with response, whether it will decay or whether it will go up. All right, so now we go to first and second order systems. Are there any questions? I see that you are quiet. It's morning. I hope you are not sick like myself. A bit of a sore throat, hard to talk. But are there any questions at this stage? Yeah.
Can you repeat what you mean by proper system?
Sorry?
Proper system.
Proper.
Yeah.
Proper system is a system that has the same number of zeros and poles. So what I mean by proper system is when, note that n is the order of the polynomial in the denominator and m is the order of polynomial in the numerator. When n is equal to m, I call it proper. When n is strictly smaller than n, I call it strictly proper. This properness is related to the important concept of causality. So causal systems would have the property that the transfer functions corresponding to causal systems are proper. So this is basically, because in physical models, physical systems, models are usually causal. I mean, if you can't find causal systems in nature, then transfer functions that we obtain from such systems, models of such systems, are proper because of causality. Any other questions? All right. So here is what you get as, this is an impulse response of a system that has a single pole. So think of this as a partial fractional expansion for the simplest system, first order system. There is only a single pole, there are no zeros. So this can be, the simplest of all systems that we can deal with. Right? So alpha here can be either positive or negative. So when we take inverse Laplace transform of this transfer function, we get this. This is the outcome. So we get an exponential in time. Now, depending on the sign of this alpha, exponential can either blow up, and that's the red curve, or it can converge to 0, and that's the blue curve. Right? So these red curves and blue curves consider two examples when alpha is either positive, that's the red, or when alpha is negative, that's the blue. So even in real, in the case of real poles, we can have qualitatively two very different responses. One response converges to 0, and another response blows up. Later on, we will classify these situations as, stable, so that's the blue, and unstable, that's the red. So if things blow up, that's an unstable system. If things converge to 0, that's a stable system. What happens when alpha is equal to 0? So, by the way, when alpha is equal to 0, you get transfer function which is 1 over s. It has a single pole at 0, right? So that would correspond just to this response, right? So because alpha is 0, e to 0 is 1, right? So you would get just this. So I would call such a system marginally stable system. Now, one interesting thing is that if you take so consider a stable response, if you take a tangent on this blue line at time equal to 0, so that's this dotted line, it would actually intersect the real axis, the time axis, exactly at 1 over alpha. That's an interesting thing. And we would actually call this thing here as a time constant. We give it a name. So by the way, a large time constant means what? It means that this response converges more slowly. Small time constant means that the response converges very quickly to 0. Are there any questions regarding this? All right, this is the simpler case. Now I want to go to the complex conjugate poles. So in this case, you have that there are two poles. So alpha is really sigma plus j omega, and also there is another one which is sigma minus j omega. Usually complex conjugate poles appear in pairs, right? So in this case, again, the response of the system can be shown to be equal to this. So impulse response is an exponential times sinusoidal function. Know that exponential depends on sigma t, so it's exponential sigma t, where sigma is exactly a real part of your pole. And this cosine depends on omega, there is cosine omega t, and omega is exactly the imaginary part of the pole. So the time response, it would depend on the properties of the pole, real and imaginary parts. So again, I plotted here two situations. The blue case is for the case when sigma is negative, right? And the red case is the case when sigma is positive. So when the real part of the pole is positive, we will see this blow up, sinusoidal function that the amplitude blows up. And when we have sigma that's negative, then the amplitude of the sinusoid would head to 0. Interestingly here, if you plot the envelope, this dashed line here is the envelope, so it just touches at these peaks, the red function, right? So it's an envelope. Now that envelope would be changing exponentially, and it would be changing exactly at the rate of sigma. So it would be exponential of sigma t. That would be the sort of form of that envelope. And also, another thing is, if we look at two consecutive peaks in this sinusoidal function, we can relate them to omega. So this sort of period of oscillation of this sinusoid is really 2 pi over omega, where omega is the imaginary part of your pole. You can also read off here, if you now look at the blue function, there is the envelope of the blue function also. So that's the function that decreases to 0, because the real part now of the pole is negative. So the envelope is e to sigma t. Sigma is negative, so that goes to 0. If we take the tangent to that envelope at time 0, we get exactly the time constant as before. So that's exactly the same thing as what we had in this case. So you take, now this blue line is no longer the response, it's the envelope of the response, and you take the tangent on that envelope, and that will be the time constant again. So we would be seeing all sorts of, so this time constant here is related again to the real part of the pole, sigma, okay? All right, so if we consider, you know, second order systems, all right, let's first stop here and ask if there are any questions, because I will now move to another representation of poles. Are there any questions at this stage? In order to follow the subject, you will need to know these things, because I will be now talking about rates of convergence, which will be related to sigma. I will talk about time constants, right, which are also related to sigma. I will talk about period of oscillations, that's related to omega. So in order to understand exactly what I'll be saying in following lectures, you need to really digest this material better. This is very important. I mean, by the way, let's just give it some examples. So if I consider a pendulum, right? So look, so this is my system. The output of this system is the angle, right? The input would be the force that I apply. What would be the impulse response? Well, I hit it with my input, which is an impulse, right? And I let it evolve. Now, how did this angle change? How did this angle change? There's a sinusoid, but the amplitude of this sinusoid, you know, decayed to 0, right? Look, this is the input. I'm applying the impulse input. So what we are analyzing here is the impulse response. In this system's case, here is the impulse. I leave it by itself. I record what the angle is doing. So it's oscillating, but the amplitude is going to 0, right? So what is the case, in this case, like what sort of poles do you think this system has? If this was modeled as a linear system, what sort of poles would this system have? Sorry? No, negative would be really okay. If it's a real pole, then I can talk about negative real or positive real. Here I need something else. Complex conjugate. So why complex conjugate? It's oscillating. But can we say more about this response, about this system? Negative real part. There you go. I just did an experiment, and now you already have an idea about what sort of model this particular system can have. You would say, well, it makes sense to model this system with a second order linear model with complex conjugate poles where real part is negative. How about the period of oscillations in this case? Well, if you measure the period of oscillation, then you can relate it to the imaginary part. So if you perform the experiment and you measured how quickly the amplitude of the oscillations decays, you can figure out sigma, because sigma is related to the time constant. Time constant is related to the envelope on these oscillations, how they decay. Period of oscillations is related to the imaginary part. So if you manage to measure these two things from this experiment, you can figure actually out the real parts and imaginary parts of it. So you know your system from experiment. That's just one example of how you can use this theory. This is not just mathematics, guys. You perform a step response or impulse response on your system, you observe the output, you can learn a lot from what I'm doing here, right? Make sense? Okay, good. I see more people nodding, that's good, that's good. All right, now for the sake of analysis, I need to do something else. I need to introduce a new way I write poles. Why is that? Well, it will lead to a very important notion of damping and undamped natural frequency. So if I have a differential equation like this and take its Laplace transform, then the transfer function can be rewritten like this. Know that I rewrote my transfer function in a very particular way. There's this psi, I would call this damping factor, and then there's this omega n. I will call this undamped frequency. So you can relate real and imaginary parts of the poles to, damping factor and natural undamped frequency. And if you actually look more carefully at, so first some terminology. So omega n I call natural or undamped frequency. Omega is damped frequency. Omega is it's just imaginary part. Sigma is the real part. Psi is damping, and omega n is natural or undamped frequency. So this is just the terminology. If you look at what's happening in the complex plane, then omega n is really like omega n and psi are sort of like polar coordinates. So psi is not in this case, it's not exactly polar coordinates because I'm not measuring this angle from positive real axis. If I measured it from positive real axis, it would be exactly polar coordinates. But I'm measuring it from the negative real axis. But still, if I just add pi, then that's exactly polar coordinates. So note that if I represent my poles, which are represented here by crosses, right? Poles are crosses, and I represent them in polar coordinates, then that exactly corresponds to omega n. Omega n is the distance of the poles to the origin, and psi, well, is this angle here. Right? This cosine inverse means arc cosine, right? Of psi, right? So these are all the relationships. Do you need to know them? Well, if you know your geometry, Euler coordinates, or polar coordinates, it's easy to derive these coordinates. It's not so hard. But why is this important? Now that we've defined this psi and omega n, we can be much more precise about the shape of the oscillatory response we get for stable systems. By the way, what I didn't emphasize here is I want to here consider only stable responses. So I'm not considering any more unstable, I just want to consider stable responses, but I want to give a more detailed sort of analysis. And in particular, I want to relate how damping factor, this psi, would affect my response. So suppose that, we have, so when damping factor is 0, then you're basically right on the imaginary axis. You will get oscillatory response. As psi is sort of, as the angle is decreased, then you will get poles on the real axis. You will get a periodic response in this case. But if psi is small and close to imaginary axis, to real axis, you will get fast, decay. So how does this translate into the responses. What's plotted here is I chose omega n to be 2 for all of these. Natural frequency is the same, meaning that the poles are really always the same distance from the origin. So if this is the distance of the pole from the origin, pole sits here, origin is here, I'm basically looking at poles that look at circle, right? They are always the same distance from the origin. And I'm just changing psi, which is basically the angle, right? So note, when psi is 0.1, we would say that damping factor is small, right? Then we have this response. Know that this response decays slowly. And then as we increase psi, right, then the response is suppressed very fast. It converges very quickly. So this damping factor is sort of physically a variable that makes sense. When I'm looking at this system, if there is more friction here and in the air, then damping factor, there will be more damping. So this will decay faster, there will be less oscillations. If there is less friction, if I've really lubricated this pivot point, so there is very little friction, this would keep oscillating longer. But the damping factor now we can relate to physical things. That's why it's very useful. Talking about damping is very useful. And by the way, I mean, it's related to polar coordinates, so mathematically also it makes sense. Okay. By the way, I'm always confused when I have Indian students, they all do this and I say, what am I doing wrong? So, Bulgarians do the same. So they say, yes. So, what, would you help me? Why not? But that means yes. So it's, anyway. So, all right. Any questions regarding this? So look guys, it's very important for you to think about this picture, how psi changes, and then think about this picture and how locations of poles would change, right? So that you can relate locations of poles to actually the response you are seeing. So you see, this gives us even more information about, you know, this experiment we were doing, right? If it oscillates more, we say, well, there's less damping. So you know that this psi would be, you know, smaller, that number. So if there is more, obviously, if you had so much damping that this just did this, a periodic response, it might happen. Like if you really sort of have, you know, certain sort of friction force here, you might in some cases, you have like an impulse and it just sort of comes back, right? You would then have that poles are really close to the real axis. It's almost like a periodic response, right? All right, so just some relationships. Time constant increases as damping decreases. Why is that? Because we said time constant is related to that tangent at the envelope, and if time constant is larger, then envelope is decaying more slowly, but that corresponds to less damping in the system. Right? Peak of oscillation increases and damping decreases. What you can also show is if you gave this system a step input and there is little damping, this system would exhibit big overshoots, right? So second order system would exhibit big overshoots. So actually this is also something, we didn't talk about this more in this lecture, but we will come back to it later when we give formulas for overshoot later on. And also frequency of oscillation increases but damping decreases. Obviously we need to, you know, fix natural frequency. And then the true frequency would be the damped frequency. So if why is this true? Well, go back and see the relationship between omega. Omega can be read out from the pictures, right? That's the related to period. If you look at the period of oscillations, 2 pi over omega is exactly that period. So you can read off from experiments omega. But omega is related to omega n, which is the natural or undamped frequency, and psi. So I'm saying keep omega n fixed and change psi, right? Then, you know, you have the conclusion I gave you, right? So this is, you know, you can play all sorts of different games here by saying, okay, if I keep omega n fixed and g to psi, what happens to this sigma? Well, that's related to the time constant. That's the first statement I had. The second statement I had was related to this term. Yeah? So understanding of these things is very important, and I'm just summarizing them here, but you can read them out from mathematics, really. You can just look at the formulas and get those conclusions. All right, so now for the big sort of finale of the lecture, look at this picture. Now, you guys really need to understand that, you know, all of these things are possible. I didn't talk about all of them in the lecture. There is simply not enough time. But you need to have this much intuition to understand that this is true. So what does this picture represent? Think about these crosses here as a pole in your transfer function. So if you look at partial fraction expansion and you have a pole at that place, then there would be a term in the impulse response time function that corresponds to that pole. Right? It will be scaled by some constant. So if you have, for instance, pole at the origin, your impulse response would contain a function which is a step function. Inverse Laplace transform of 1 over s is step function. So if you have a pole that is real and with negative part, but negative real pole, you will have, you know, if the pole is close to the imaginary axis, then the decay, there will be decay, but decay will be slow. If the pole is farther away from the imaginary axis, then the time constant will be smaller and this will converge faster. So just think about it this way. Anything that's closer to imaginary axis but on the left-hand side would converge, but the closer to imaginary axis it is, the slower it would converge. So that's what all of these guys show. If you have, you know, pole at this point, it would converge, but it would converge slowly. But if you have a pole here, it would converge with the same frequency. By the way, omega here is the same. So this guy would oscillate at the same frequency as this guy. But this guy would converge faster than that guy. Right? If you go up, right, then omega changes, and then the higher you go up, the oscillations would be faster and faster. Period of oscillations would be smaller and smaller. But they will all decay. Everything on the left-hand side would decay. Now, if you have a general transfer function, then its response to a general transfer function would be a weighted sum of responses corresponding to these poles. So how about the right half plane? Now, if you look at anything on the imaginary axis first, well, anything on the imaginary axis would never decay to zero. If we have a pole at the origin, we already talked about it, that would correspond to the step function in the inverse Laplace sense. If we have a pole at the imaginary axis here, it would oscillate at this frequency. This is exactly the frequency of oscillation. So imaginary part of the, you know, of this pole would be exactly related to the period of oscillations. Now, the closer we are to the origin, the slower the oscillations. The higher up we go on the imaginary axis, the faster the oscillations. But they would never decay. It would just be sustained oscillation. What would a pole like this correspond to? It would correspond to this system where there's no friction. It just keeps oscillating. There's no friction, right? So that's basically what these poles correspond to. Now, if we have positive real poles, then obviously that would correspond to blowing up, right? And we did consider this case. We did consider this case for a real pole. So we did consider these cases and these cases. That was the first order system that we considered, right? We talked about this. So, but if we have complex conjugate poles, then, you know, their oscillations, if they are in the right half plane, they would blow up. Amplitude would blow up. At what rate does it blow up? That would depend on the real part. So here it would slowly blow up. The closer we are to the imaginary axis, the slower the blow up is. And then, you know, the further away from the imaginary axis we are, the faster the blow up is. And then if we go up, you know, in the frequency, you know, there will be faster oscillations. If we go closer to the real axis, it's slower oscillations. So you guys need to really know this very well, right? Because this is just analysis. I'm just telling you, if this happens, then you get this. But what you would be dealing with in this subject, I will tell you, achieve maybe this behavior by designing a controller. So you have a plant, you want to close the loop, design a controller so that you achieve some of these behaviors. So you have to go a step further and design systems that behave in the way you want them to behave. All right. So this is just a summary. I already explained all of this. I just want to give you a preview. In the next lecture, we will go even in more detail and look at how locations of poles are related to overshoot, rise time, and settling time for second-order systems. So I will concentrate on second-order systems, and I will give you even more precise location of poles for the second-order system so that you have overshoot less than 10% or 20%, or rise time less than 1 second, 0.1 second. So we will be really able to then translate the features of step response into locations of the poles for second-order systems. And this is the first step in design. The first step in design sometimes is translate features of step response into locations of poles. And then the second step is we'll design control that achieves this. All right, so what we did today, we looked at impulse responses of linear systems, and we saw that it's a sum of some basic functions. We presented all these basic functions, and then we concentrated on first-order systems and second-order systems, right? But we also presented the general case. So you need to understand the material at this level. Right? Any questions? All right, thank you very much. I'll see you this afternoon. Thanks.
We will have conjugate complex poles like alpha equals sigma minus j omega. We only consider the real part of it, but I don't know why don't we consider the imaginary part?
If you remember, I was telling you in the last lecture, if you add two complex conjugate poles, you get the real function. It's the same.
And the imaginary part of the conjugate complex poles potential.
Yes. So that's why it was just real parts. But what I could have done, I could have said, let's consider a pair of complex conjugate poles, and then that would be the function corresponding to those.
And for our second-order system, we have the damping factor and the undamped frequency. But I just want to know how can we get the omega and the phi directly from the model.
Well, you need to transform the representation of the poles into the form that I gave you. So if you have s squared plus 2 times psi omega n s plus omega n squared, well, from that form you can read out directly psi omega n. But you need to just represent your polynomial in that way.
And remember, this relationship is that omega square plus sigma square equals omega n square, and it represents a circle.
Yes.
But I just want to know, is there any physical explanation of this relationship? Why it plus it?
Let's take it outside. There's another picture here.
这下节必定有课，你以为吗？